a little bit tedious, but it's worth it because later on, once we go to the numerical implementations, we only need is one single piece of the Maillard function. We can solve for all types of the Kepler's problems. And so we see. So the motivations, if you like, you can write it up. Is we wish to learn the only using only formulation, only one equation that can solve for Kepler's problems. Okay. So the method is this. So the method, we start from here. We start from the formulations of the energy, and on one side that is the minus mu over QA, on the other side that is V squared over 2 minus mu over R. Okay, and for V, we want to, hopefully we can convert into the radial, the polar corner system. So here for V square, we can replace by this R dot square plus R mu dot square. So that is, this is express velocity in the polar coordinate system, where V equal to VR plus V theta, and VR equal to R dot ER. And V theta is R mu dot E theta. Okay, the nu is our true anomaly. The nu dot, that means the derivative, time derivative of the true anomaly. So we plug in here, and that's very straightforward. R dot square plus 2 R mu dot minus mu over R. Okay, so from here you can see our intent is try to show, hopefully using the R dot related functions here. Okay, so here once we have this one, then let me get the expressions R dot square. So that means here I want to focus on that term and move the other two terms on the other side and do an arrangement here. Okay. So that one is simply equal to minus mu over A plus 2 mu over R, and minus R mu dot square. Okay. And this one, we can do a little bit more rearrangement here. This one, actually, I want to express is this. Let me do diversion a little bit. This one basically is equal to this one is equal to this. Let me multiply the square root inside with r squared. Okay, you can see here I multiply square here. I want to emphasize. Okay, because in the bracket I have the square, r squared here, so to make this equal, so that means I must divide by that one. You good? And why I want to make up the terms inside the bracket by this? Because that's related to the p. If you remember, the r squared times mu dot is our h, angular momentum. Okay, so that becomes this one. And angular momentum squared basically is equal to mu p r squared. Okay, so basically this one, let me rewrite. So therefore r dot square equal to minus mu over a plus 2 mu over r minus mu p over r squared. And this is not that useful yet, but here let me box it as equation 1. We're going to use it later. And you may ask me why we want to spend time kind of doing this kind of weird derivations. And again, our goal is to come up with a universal equations for the Kepler's progress. And that's the equation 1. And I can tell you in total we will have 10 equations and to do something. Then the second equation is this. That comes to the most weird part. Define the derivative of the universal variable. Okay, and this is the first time to show up the universal variable that play a central role in these formulations. Okay, and this variable in our textbook simply using the capital X. And to here in my writings here, allow me to use this one, and I think this is the capital Kasi in Greeks. Okay, so in my notes in my writing, I using capital Kasi, but again in our textbook, if you have a textbook with you, you can see that textbook using both capital X. Okay, so hopefully you know what I'm saying. So probably today we stop here, and then we start from this one next time. Okay, thank you.